All right, everybody can hear me okay?
Yes.
Great. All right, so welcome to the class. I just sent an email to everybody to make sure that they have the link, but yeah, I think Moodle takes time to react, so maybe the email hasn't been sent yet, but anyways, here we are. So happy to see everybody there. Yeah, so why don't we already go over the syllabus to explain to you what this class is all about. So let me share my screen. Okay, so if you are looking to learn some math, you're at the right place. Otherwise, I advise you go back to sleep. So yeah, my name is Nicolas Lepage-Chaussé. I was in France for the last 8 years, 9 years. And now I've decided to come back to Montreal, which is my hometown in some ways. So yeah, I'm happy to be here. Okay, so this is my email, my office. I'm going to have online and offline office hours because, you know, it's COVID, so I prefer to have more than less. So if you want to reach me, you can on Monday or Wednesdays from 4:15 to 5:30 on Zoom with this link, or in my office at the same time on Fridays. Or you know, if you're in a big rush, write to me and we can set an appointment, no problems. So the lectures are on Fridays. Tutorials are just after the lecture, but they start in 2 weeks. They are from 11:45 to 12:45 online too. This is the textbook. I have, so what happens is is at the library, they have some chapters that you can look, but really, if there's something good that you can do for yourself in your career as an economist, is to buy this book. It's very good. And then you can have all the chapters. Yeah, so a few chapters are available at the library. But yeah, it's very useful to have it. I'm going to follow it very closely. So yeah, so the person who was giving the class last time didn't give me a lot of information, except from the fact that this book was newly news. So I'm going to follow it quite thoroughly. Yeah. Yeah. So why do we have this class? Well, we have this class because economists don't like to have to teach math while teaching economics. Thing is, though, it's learning economics is a very good way to learn about math because you apply your math knowledge to some easy or quite easy examples that we have in economic theory. But still, so we're going to have some mixture of economics and math in this class. But basically, it's an introduction. So we learn about sets, about yeah, basic arithmetics, matrices a lot, determinant, matrix algebra, all this good stuff. So this is coming later. Yeah, so you have basically I'm going to start at chapter 2 simply because the meat of mathematics in the textbook starts at chapter 2. So what is chapter 1 is just the introduction. So it's what we're doing today. Grading scheme. So if you have downloaded the syllabus before yesterday night, then you don't have the right version because I have chatted with the last TA, and she told me how they used to do it last time, and they used to have 3 homework assignments. So I think it's a good way to stick to a battle proven strategy for this class. So yeah, 3 homework assignments, 20%. that you do hopefully in team of 3. But if you can't find a friend, or if you hate working with people, just do it by yourself. I won't be mad. And then, yeah, 2 exams on Moodle. So 1 midterm, 1 final. So I try to have 1 homework before the before the midterm, and then 2 homeworks after it. And so what will happen in the plan is I upload the exam. Then you do it on your own, then you scan it, then you upload it to Moodle, and we grade you. So you do it on paper. So yeah, I could create some questions that are automatically graded on Moodle, but yeah, first of all, it's a lot of work for me. And second of all, students really don't like it, because it means that even though you're 95% correct in your understanding, if you make some silly computation mistake, then you have, if it's a multiple choice question, for instance, you just get the question wrong and there's no recourse for you. So I think it's better to have it this way. Yeah. Yeah, so all exams are open book, non-proctored, but we trust you that you do them alone. Yeah, so this is the tentative schedule for the assignments. So everything here is to give you as much information as I can, but since it's the first time I give this class, I may adjust if things don't go well, if things take too long or whatever, or if you have stuff that goes wrong in your life and you say, oh, please, sir, could you postpone this homework or something? Yeah, so I was thinking of giving you 1 week to do the homeworks, because anyways, it's not good to drag work too long. It's good to get it over with. Yeah, so you can shift the weight of the midterm to the final. But then if you miss the final, it's bad news. Okay, so course outline, introduction. So first of all, what are economic models, variables, functions, this type of thing. Then static analysis, partial and general equilibrium models, polynomial equations, substitution and elimination. This is, if you think, oh, but I already know all this stuff, I know it's normal. So you can pretty much surf over that part of the class, and it's take it as a good thing that you don't have to worry already about the stuff, but it's to make sure that everybody is on the same page. And then we start with the more interesting parts. So matrix, algebra, matrices, Cramer's rule, determinants, rank of a matrix, then comparative statics, all these things. And then some optimization. So yeah, this is something I know quite a lot about. So it's good that if you have questions, well, I know some about, but yeah, in any of the topics, some of you might know more, I don't know. So it's always possible that something I say is not perfectly precise. Of course, it's my job to be as precise as I can. But whenever I write something, if you think, oh, it's unclear, or there's a mistake, or there's a spelling error, or whatever, feel free to say it. So you're going to sound like a genius, and everybody's going to admire you, and everybody is going to be so happy that you ask the question, because like half of the class is going to be confused, but they're too scared to say it. So if you are confused, it's very good to ask the question. And if you are confused by the material, anyways, there's a tutorial, weekly tutorial, and yeah, office hours, so you can come and ask me questions about that. All right, so questions, fears, comments about how the class is working? No, all clear. Okay, so by the way, if somebody's trying to speak, you might be muted. So, but yeah, by now I think we should have some working knowledge of how of Moodle. Okay, it's not Moodle, but Zoom. So how is this class going to work? So I thought, do I create slides or not? Well, first of all, I don't have time to create slides right away. Plus, I think it's good that we just work as if we were in front of a Blackboard, but it's not going to be a Blackboard. It's going to be a computer screen. But I advise you to how to go about for the class. I advise you to write down everything that I write down so that you can make sure you understand what's going on and you follow what's going on. All right, so let me share my screen. So let's say this is one. Let's put this here. So I'm using this. If you don't know what this is called a Scientific Workplace. I think it's the best old tool that exists for LaTeX. But it's super old. So the last version of this version is 2005, I think. And I think the company went bankrupt, but they are, as far as I can tell, they're trying to release their source code for this online. So it becomes an open source project. So, and at least it can evolve, but because the 2005 is like ancient history. Okay, question there. Will taking math 204 help? Yeah, any math help, of course. What is 204? In your algebra 1? Yeah, of course. Actually, I think it's going to overlap quite a bit with what I'm doing. So is that given at the math department or? Okay, yeah. Yeah, so it might be even better than this class, who knows? So this is, of course, the focus is pretty much different. So in math class, you learn math, and there's a great emphasis on rigor and proofs. So here, I'm not here to make sure that you can prove theorems. I'm here to help you as much as possible, and to help my colleagues, economists, to make sure that they don't have to waste time learning math to you. So yeah, the emphasis is going to be on application and especially economics applications. Yeah, but you know the content still is quite similar. And by the way, if you learn some stuff in that class and you think, oh, what I'm teaching is not precise for whatever reason, then tell me. Maybe you can even improve the content of the class. Okay, introduction. So everybody can read what I'm writing, right? Yeah, Zoom is annoying me a bit. Okay. All right. So why do economists need math? So for many reasons. So why do it for the same reason that science in general needs math? So why is math so useful? So first reason I would say is uniformization of the discipline. So before we had the discipline was very literary. So say for instance, Adam Smith would write his philosophy books, and then, oh, by the way, I'm going to write a book about economics. But you know, in his mind, it was just a part of natural philosophy or ethics or philosophy in general. So he would use a lot of words to describe his ideas. Yeah, so I would say before. So things were intuitive and literary. So you had different schools. Like the Austrian school, the Marxist school, and so what you would tend to have in the exams is, oh, please write me an essay comparing the view of Karl Marx to Friedrich Hayek, and in a lot of work. But then, so what's the problem with this? And by the way, in France, they call it the belle économie, so the nice economics or the beautiful economics. So classic, the classic economics. But what's wrong with this? Well, it's first of all, it's hard because some people write in German, some write in French, some write in English. So you have to learn the language to interpret what they're saying. And yeah, everything is open to interpretation. So you can spend half of your time saying, yeah, but what's he exactly meaning there? Does that make sense? So it's very hard to have a common set of ideas. But now what do we have? Especially since yeah, after Robert Samuelson. We have a uniform, so we have, yeah, math standardized everything. So now we don't have many different sentences to express the same idea. We have one formula, and this formula works in every language. And that means that if you, especially for very standard topics like microeconomics, if you're here in Montreal in 2021, or in Japan in the 1990s, or in France in 5 years, no matter what, you're always going to learn exactly the same thing. Microeconomics is microeconomics. And so this is how we make progress, is we establish something that is extremely solid, that is based on common ideas. And instead of writing a whole book chapter, we just write a small model, and everybody understands what's going on there. So the second thing, of course, is to avoid mistake.
Excuse me. So sorry. Yeah. Could you add your wire to your headphones? Because I feel there's a bit of background noise that's making your voice a bit unclear.
Oh.
Or maybe you have like an option.
It's the first time that this happened, but
it's only a bit unclear. It's not really bad, but it would just help in the long run. It's okay if it's not possible for this.
Yeah, I don't have a headset. I'm using my computer's microphone.
Okay.
So, and I guess there is no there's no background noise since I'm using the headset. So the headphone.
Okay.
Well, I'm sorry. I'm going to look into that and hopefully rectify the situation for next class.
It's a bit. It's mostly fine. I can understand you. It's just a bit. When I put my headphones on, it's a bit.
I'm going to try to be closer to the computer.
Okay, great. Thank you.
So thanks for mentioning that. I'll note that here. Okay. So yeah, second is to avoid the mistakes or reasoning mistake. So why do I do that? Do I write this? Well, because economics can be complicated. The world is complicated. And sometimes we have some intuition of how people go about in their lives and how they think. But it's not super clear if really one thing is going to influence the other thing positively or negatively. It's sometimes it can counterintuitive things can happen, and if you have to write a model, then it forces you to be clear about so what are your assumptions. And then, so what are the logical consequences? So economists sometimes say you write the model, then burn the math. So why do you burn the math? Because at the end, what we want to convey is ideas. So we don't really need to have the math, but we wrote the model. So we are sure that so what we're saying is not stupid, makes sense, it's coherent. And then we don't really need, especially for if you're going to talk to the prime minister or to the press, you're never going to write them equations. They're not going to understand anything, but at least what you're saying, you're sure that it makes sense. So it's a bit linked to the first one. Then, of course, with the model, but of course, we don't really burn the math, we use it a lot. And then we can make quantifiable prediction. So once we have a model, then we can use it to say something like, instead of saying, oh, when we get out of COVID, the situation, the economic situation should improve. Yeah, but that's not super precise. What we can say is, oh, I predict that GDP is going to increase by 3%. So that's a precise statement that you can only do with math, of course. And then you can also test theories rigorously. So what do I mean by that? Well, if I make my prediction and it's wrong, and instead of increasing by 3%, the GDP decreases by 3%. So what does that say about my model? Well, it's not so good. So yeah, test prediction against reality and reject wrong. So of course, that's in theory. In practice, people get around bad prediction all the time. But if you really want your model to, if you really like your model, then instead what you can use is you can use math to make your model sound scientific and lie with authority. I'm saying that because we can always write down even a mathematically sound model that predicts all kinds of weird things if we make weird assumptions. But of course, it's a bit more difficult to do that than if you don't have any math. So yeah, the the state of the art in terms of testing theories is, of course, randomized control trial. So some of you know who won the Nobel Prize recently for that in economics, 2019. No? It was Duflo, Banerjee, and Kremer. For introducing randomized controlled trials in economics in a formal fashion. So randomized controlled trials have existed in many disciplines. For instance, in medicine, they do that since the first part of the 20th century. But it's super difficult to do it in social sciences, and yet these people they said, no, we can do it, and the gain that was made by the discipline by introducing this is just outstanding, especially in development, which in which discipline they work in. It's awesome. Yeah, if you like this kind of thing or development, it's unavoidable. Yeah, and lastly, compare things that are not easily comparable. So I would say it's a cost analysis. So what do I mean by that? Well, if you ask a doctor, should I increase your funding? It's going to say, of course, I save lives. There's nothing more precious than a human life. And what do economists respond? They say, no, actually, it's something that we can quantify. So should we invest 10 million to save one other person's life, or increase the funding in education, for instance? That's a question that we have to ask. And if we cannot have some benchmark to compare two things, I mean, if we don't have a unit of comparison, then there's no way to say, how do you compare one life or 10 lives saved, or one other bridge, or one other university. It's impossible to compare these things. Yet, if we have a common framework to describe, okay, this is how we can quantify and value stuff, then we can have statements about this. And so you can say like something like, oh, is it better to take the risk of a vaccine or to take the risk of having COVID? Is it better to take the risk of having a nuclear plant or another dam, for instance? So in discussions, it's usually people who speak the loudest that gain the upper hand and win debates. But in economics, you can just say, no, I'm going to stack what is the probability of dying from COVID, what is the probability of nuclear accident, what is what is the value of a human life? So it tells me if I should impose vaccines or not, all these things. So this is all these things that are gained by using math in economics. All right. So that's for introduction. So now, how is the class going to work? Well, I already said a bunch of things about it. So first of all, yeah, emphasis on application rather than proofs. The objective is to teach math, not teach economics. But as I said, economics is a good context to learn math. So what do I mean by that? Well, so people have this idea that professional mathematicians, they just have a very abstract mind and they're able to just prove some general theorem and then apply it to everything. But that's not how things work. If you ask them, what they do is they say, oh, I have this idea, but I have no clue if it's right, so I'm going to try it on some simple example. And after they tried it on 4, 5, 6, 7 examples, then they can start to gain some intuition as to how things are working, and they're able to think about the theorem they are trying to show. So they're humans, they're exactly like you. So when you're learning about mathematics, the thing to do is to start with simple problems, to reproduce what I just did in class, and to make sure that you can do all the steps. So, and just when you're really familiar, then you can move on to more complicated things. but it's so we always start with the same thing. We start with something easy to gain intuition, and at the end we can. So students sometimes they say, "Oh, I'm so smart, I'm not going to learn anything," and just 2 days before the exam, and I'm going to cram and learn all the examples by heart. Well, joke's on you, because by learning all the examples by heart, you're actually learning the material. That's how you learn that's how you make connections, and it becomes a second nature for you to just do this thing. And you pretty much, exactly as predicted, you do very well in the exam because you're fast and you have developed this intuition. So that's how you do it. You don't, there's no other way to do it. You do exercise, do exercise, do exercise, do exercise. By the way, so I'm a violinist, and that's exactly how we do it. We don't start by playing a piece at tempo like at the concert. We just start with small section of the piece, and we go slowly. We play them 100 times, and then when the fingers are working well, then you can add the pieces together and go faster. So it's exactly the same thing. Yeah. And so this is how mathematic reasoning works. So you start with, say, 1, 2, 3, and then you say, oh yeah, but maybe it works with any number. So let's try with A, B, and C that are, say, in the natural numbers. So we're going to define what this is later. And then we can say, oh yeah, but what if they are in the reals? What if they're in the complex numbers? So you just add complexity to it. And then you say, oh, why not matrices? So this is how math works. We start with something super concrete, and then you realize that what you did for something concrete works for something more abstract, more general, more general, more general, and you build up from there. Oh yeah, by the way, if you're uncertain with symbols, ask me. So I'm here to do that. So if I use some weird things that you are unfamiliar with, just ask me. So by the way, these are natural number, real numbers, complex numbers. We're going to see what they are later on. So yeah, so that's about it for introduction. So we can start with 2 then. Question about what I just said? No, all clear. Well, I suggest you do ask question, because otherwise it's not that fun. But anyways, I'm going to ask you question. Oh yeah, that's something else I wanted to say is I like to interact with you. Otherwise, there's no difference between just a pre-recorded lecture and this. So if I want to believe that I'm useful for something, then we have to have something that's interactive. And if nobody answers, then I'm just going to pick people at random. So yes, get ready. If you don't know the answer, just say, sorry, I don't know the answer, and that's it. There's no shame in that. But if you like to know the answers, then a good thing might be to read the chapter beforehand, so you're ready for the class, and then you sound like a genius in front of all your colleagues when I ask you stuff. All right, so let's go with chapter 2. So what's a model? Any idea?
An attempt to rationalize what we have seen.
Oh, that's a very interesting thing. So attempt to rationalize what we have seen. I really like the word attempt because yes, what we have seen is reality, and we never describe the whole of reality. Otherwise, it's not a model, it's just the world. It's just the universe. So how I like to think of it is the models are like maps. So what do you have on a map? Well, first of all, you choose what you're going to put on the map, which region. That's what you focus on. And then you can say, oh, what actually interests me is roads, or is altitude, or it's water, whatever you choose. Then that's what you draw on your map. And you're able to then omit what you don't need. So there's I think it was Feynman who said, yeah, that so science is the or Feynman, or yeah, I can't remember exactly, but basically it's what we can so model or science is the art of omitting what can be with advantage omitted. So what we can neglect, so we can focus on a few ideas that are key to describing the world. So here's my definition. So model is a set of ideas describing a phenomenon. So it can be, I can describe it, as I said, with words, with a drawing, but in economics and science in general, we usually use math to describe it. Yeah, so you could say that in disciplines like history, for instance, then they don't really use math, but still there are some historians that are starting to use ideas from statistics and from, say, Bayes' theorem to quantify their level of certainty or uncertainty about certain historical events, for instance. So really, math is just creeping everywhere. And just as a general term, general idea, something nice I've heard this week. So some person was saying that the 20th century was for people who make good speeches, but the 21st century is going to be for math and code, because once you are good at quantitative thinking, then it just gives you a superpower to interpret the actual world with all the data that we have today. And you have a very good, I would say, bullshit detector when somebody tells you something that doesn't make too much sense. So yeah, it's just great to learn that. All right. So what are variables? So I'm not going to ask you because it's somehow super intuitive, but also a bit tricky. So I would say that it is something which changes. It typically reflects different observations. So there's only one thing that never changes. It's constants like pi or like or 1, 2, or 3. But within models, we have these different ideas of what variables are. So usually we have something that we mean something that changes between examples. So if we say that a model is to rationalize a phenomenon that we've seen, so it can be something like, oh, I think that tall people weigh more, for instance. So that's your model. And so what is your variable within this model? Well, people vary by height, and then if I measure their height, then I'm going to have an information about how heavy they are. So what are the two variables here? That's height and weight. And note that the specific way in which this relation occur is also something that I have to estimate, and there's uncertainty to it. So you could say it's a variable too, but within a model, we say that, yeah, this is what we're going to call parameters. So let me give you an example of variables. So firms vary in terms of ideas. Firms vary in terms of what?
You could say something like production.
Yes. And I could add revenue, profit, etc. People vary by in terms of, well, we said height or weight, but of course they vary in terms of. So what do we care about today a lot?
Vaccination.
Oh, yeah, that's true. What I had in mind is income. So we care about the income distribution. So then the variable that really interests us is income, and it's how widely spread it is, or in mathematical term, you would say what is the standard deviation of income. If you say that income is log linear, for instance. So working hours, etc. And you could say that countries vary in terms of what?
Population.
Yeah, population. Could add GDP, landmass, technology level. Etc. So this is the meat of what is a model? A model is links between these different variables. So these are all the variables, and the model is going to try to explain what's going on between them. We have two types of variables: exogenous variables and endogenous variables. So what's an exogenous variable? Somebody has an idea? Oh, sorry, that was very soft.
variables that are not explained by the model.
Yeah, so not explained by the model or determined outside the model. And what is then endogenous variable?
That can be explained by the model.
Yeah. This is what we're trying to explain. So if we have a theory about, let's say, GDP and population, and so we can say something like, oh, countries with large populations have a large GDP. So if I state it this way, then what am I saying? I'm using population as the exogenous variable. I'm saying if a country happens to have a large population, for whatever reason that I don't care to say, then it's going to also have a large GDP. But I could also say the reverse, of course. All right, so that's exogenous and endogenous variables. Then what's a parameter? Within a model. This is more tricky.
This might be too vague, but it's like the extents within the model that you can go to.
Yeah, I agree that it's a bit vague, but yeah, it. All right, so somebody
Is it
has
just
a,
the,
yeah,
is
go
it
ahead.
just the inputs? No, I'm confused.
No, it's when I say it, you're going to think it's obvious, but I know that it's not obvious right away. It's a constant within the model. It's typically what we are trying to estimate. So it sounds weird because we're saying it's a constant, but within the model, and we're trying to estimate it. So, but when I write an example, then you're going to think it's obvious. Yeah. So what do I mean? So for instance, consumer demand. So that's that I have a model about this. So can somebody tell me what is typically the model I have in mind about consumer demand?
I would say the quantity demanded is equal to quantity supplied.
That's market equilibrium, right?
Right. Yeah.
So it's even before that.
Quantity demanded will increase as the price decreases.
Yes, or the other way around. Quantity demanded decreases if the price increases. Yeah. So, yeah, consumer want to buy more. So that's a model. It's very simple. You could say yes, but usually we see supply and demand and market equilibrium and all that stuff. Yes, but still this in itself is a model. It's an idea how I think people react in the world, and something that I can try to quantify. So an example would be something like quantity demanded equals -3p. So what is the exogenous variable in that?
The price.
Yes, p price. What is the endogenous variable?
Quantity?
Yes. Well, yeah, I'm just thinking. So, when should I would like to take a break at some point because it's very long. Yeah, so we started at. So should we like take a break at 10? How's that sound? Like
Sounds like a plan.
yeah, okay, all right. So break at 10. So endogenous variable is QD, and what is the parameter?
-3.
Consumer demand?
Yeah, it's
Oh.
-3.
Okay.
So -3, it's not really constant in the sense that like pi is a constant, for instance, but within the model, it's a constant because what I'm saying is if p goes up, QD goes down. This relation is always going to be the same for all the observations. By the way, it may not always be the case. Yeah, in some instances, you have even parameters that can change if the value of these change, but it's some other way of saying the same thing. Yes, Mr. Gilström.
If QD equaled in your example -3 +5, would the +5 also be a parameter?
Yes.
Okay, thanks.
Yeah, I could have +5 here. Of course, this would be yeah. This would have some. It would be not be 5. It would have some units. So like 3 has some units too, because at some point I'm describing a quantity here. So a quantity is not equal to a price, and it's not equal to a constant. So this would be +5. I don't remember units, for instance, if QD is in units. But yeah, it's a constant. Now, is this model true?
No, because as the price would increase, the quantity demanded would decrease. Oh,
Yeah, but
sorry. Yeah, no,
it's-
that makes sense. Never mind. So yes, it is true.
Yeah, well, okay, it might be true. So what I had in mind is it may be true in some instances, more or less, but false in other instances. So it's all models are false, but some are more false than others. Yeah, and by the way, here I could have, to be very coherent, I could have said that QD and P greater than 0. Greater or equal. To be perfectly coherent. So that's a different model than the other one. Here I was claiming that you could have a price so high that quantity demanded becomes negative, which doesn't really make sense for consumers. So yeah. Oh, by the way, there are discussions there. Yeah, okay. So I'm going to try to monitor the discussions. In some classes, I have like over 300 people, and then it's just impossible for me to monitor the discussion. But yeah, so I'm going to try and look at it. And this is even true for these things. So there's a sort of a debate in economics whether randomized control trials are the best thing ever or just applicable in some super tiny context. For instance, you know, if I'm in some African country and I subsidize bed nets for mosquitoes, then it's good because people are going to use them more, for instance. So how does this knowledge apply to other contexts, other countries, other income brackets? My personal opinion is it's awesome that we can just say that we can discover something about a specific country in a specific time period. And then it may not be a perfect model for other countries, other time periods, but it gives us some intuition of what works or not. And it gives us the opportunity to reproduce the same experiment elsewhere to see whether it still works or doesn't work, for instance. So these control trials are extremely good, but it's true that their applicability is limited. But at least when we do find some effect, we are quite confident that the effect that we found is a good one. Okay. What does this formulation assume? So I have written it this way. And I'm trying to estimate -3, for instance. But did I make some assumption within the model?
You assumed that nobody would buy it because basically you got no positive quantity if P is 0, quantity is 0, and then if P is 1, it automatically becomes negative.
Well, that's just, I just realized that I wrote a very stupid thing. So imagine it's 10 minus 3p. Okay, so yes, sorry about that. Yeah, that was a very stupid assumption. Wow, okay. Yes, so what I had in mind was, yeah, okay, so that's, so I'm never going to, so is this model true? No, it's totally wrong, but that would be more true, I would say. Yeah, but so what I had in mind is that I have assumed a linear relation between price and quantity. So you see that even if I'm trying to estimate the -3 here, and I get something that looks like it makes sense. Does it mean that I'm done? I have found the reality? No, because before, when I decided to write down my model, this is how I wrote it down. I wrote it down in a linear fashion. Maybe it's quadratic. Maybe it's some other more complicated function, and probably it is. But do we write them this way? Well, we write them this way because it synthesizes the ideas that we care about, and it's easier to work with linear systems than nonlinear ones. Yeah, but bear in mind that we are always somehow making assumptions when we write down models. Okay, so just for fun tonight, try it with this. So do the same thing. Just what's a exogenous variable, endogenous variable, parameter, and all that good stuff. Okay, so that's just for terminology. So any last questions about this section? Let's see, this is more.
So a parameter is just in this. Oh, so it is just a constant. That's all.
Yeah, within the
Oh.
model, it's something that is the same for everybody. Yeah, so here, for instance, it's -3, and it's not a variable that changes between observation. It's a description of my model.
Just another question regarding the parameter. So like beta in a solo model would also be a parameter, right?
Say that
Like
again?
a solo, so like beta in a solo growth model would also be a parameter.
Yeah. Oops, I thought solo model last year, but now what's the beta again?
Sorry, beta like in the sorry in the adjusted model with the human capital thing, where B is the efficiency to use human capital, or I don't know, the
Oh, the
efficiency of
technology.
technology. Yeah.
Yeah.
So that would also be a parameter.
Yes,
Okay.
exactly. Yeah.
Okay, thank you.
Yeah, parameters is what we're trying to estimate. So when so I assume that the model is something like QD equals A minus BP, for instance, and what I'm trying to estimate is A and B. Here I'm describing a theoretical way in which the demand should work. And then I'm saying, oh yeah, but let's try to estimate this for Canada in 2021. So let's try to put values here. So these are the parameters.
So what's the difference between a parameter and an exogenous variable then? Because if you write it out like how you just had, aren't A, B, and P kind of all just exogenous variables?
Yeah, it's a good question. So a variable changes. So if I have this model, for instance, I can have subject 1. And that subject is going to have 2, or maybe yeah, time period 1. So I'm going to have a price of 1. So the demand is going to be 7. And then time 2. So I have a price of 2. And then, so I'm going to have a demand of 4. So what was the exogenous variable here? It's 1 or 2, because it changed. And what was the endogenous variable? It's 7 and 4, because that changed. And the parameters are something that remain the same between the two observations I took, so -3 and 10. Does that make sense?
Yeah, thank you.
All right, so let's go to sets. Sets of numbers, sets. especially sets of numbers. So the natural numbers. So you can write it down as a n with a double line there. Or sometimes you see it written this way. With just boldface. Yeah. If somebody has a good word processor, then they can have this. Otherwise, you can just write it this way. And what are them? They are 1, 2, 3, 4. So this is the first thing you learn when you're a kid. You learn to count, and that's included in what? Somebody knows? Well, it's included in a lot of other things, but the more interesting set.
It's included in integers, real numbers, and even
Yes.
complex, I think.
Yeah, integers, which we write. Let's see. Which add -3, -2. +1, 0. So 0 was maybe some of you have heard this was a huge innovation because otherwise it's kind of unclear how you think about so like in the Roman Empire they would say something like, oh, how many do you have? Well, I had 5 and I sold 5, so I have 5 minus 5. But so once you really say, okay, this is just a measure and 0 is just some point on my measuring scale, and I could even go to negative numbers, then it just opens your mind to, but you see that it sounds more abstract because especially in economics, so many things don't make sense if you have a negative quantity. So you don't demand a negative quantity, you don't produce a negative quantity. So that's something I can say about economics is oftentimes you would say something like, so I used to teach in some statistics school where students were so good in math, like some were better than me. And they would sometimes they would say something like, oh yeah, you wrote this, but I cannot solve because I don't know if the firm produces a positive or a negative quantity. Like, yeah, but it's not a math class, so we're talking about science. And if I write all the assumptions about all the variables, at some point it would take you a half an hour to read the exercise. So that's what you have to keep in mind when we do economics. Is economists at some point they say no, but you know we know what we're talking about, so production cannot be negative, for instance. So I'm not going to waste time telling it every time, but you know it's always an assumption that's in the background. All right, and this is included in the rational that we write. Oops. So what are the rationals? No idea. It's those that can, yes, no? It's those that can be written as ratios. So 1/2 or I don't know, minus 34 over minus 13. Well, this is getting small. I should make this larger. Yeah. Or 4 divided by 1. And these are included in the reals, which we write are, which includes things like pi or e or 2. So these three we use often in economics. Now this we start using less often. Or E, you could use it in many places, but we could use any basis we want. And oops, as was said, so this is included in complex numbers. Which we write C, which are something like 2 plus 3i, where I is square root of -1. And this is not useful in economics. Although I say that, but in some growth models, for instance, when you have, so if you have some dynamic that moves like this, for instance, I don't know if population and resources increase, then population decreases, then resources decrease and everything. So you have these sort of models that that can be described, and their dynamics sometimes may be described with I too. Yes. Question?
Yeah. Wouldn't the pi and e be considered the complex numbers because, like, they're decimals that go on forever?
Oh, that's the reals.
Oh, okay.
Yeah, the reals have can have decimals that go on forever. Yeah. Pi equals. Oops. And this goes on forever. Yeah. So, so these are the reals. And yeah, as I said, we don't use them all that often, but sometimes E we may use it. Pi, not really much. Although at some when I first started teaching, at some point I had the urban labor economic class that was extremely advanced, much too advanced for the students, in my opinion. But anyways, they were very good. So I gave them a circular city, and I asked them questions about about that, and they had to remember how to compute the area of a circle. So that was a whole lot of fun. They didn't really enjoy it all that much, but don't worry, I'm not going to give you difficult questions as like that.
Hey, sir.
Yes.
You wrote pi wrong. It's 3.14159.
Oh yeah, sorry.
Yeah, no problem.
Oh, by the way, in movies, be careful. A lot of time you can look at somebody super smart who looks like he's writing pi, but if you look at the digits, then you can, and you compare it with pi, you say, oh no, that's impossible. This doesn't happen. This doesn't happen. So yeah, sometimes people write it wrong. So and they take advantage of the fact that people don't really know a lot of digits of pi. But I can know pi until 5. I just know these 5 digits, and I don't know after that. All right. So a question about this? No, so okay, so we can have a break, and then when we come back, we can continue with the sets. So let's say we have I don't know, 10 minutes break maybe. So 10 past 10, we can come back. Okay, can everyone hear me?
Yes.
Okay, good. Sorry for the 3 minutes delay. Okay, so let's start the more challenging part. So sets, what are sets? They are a collection of objects defined by enumeration. By enumeration or definition or description. So for instance, S is a set, and we represent this with these curly braces. Yeah, that's it, right? So it can be 1, 3, 5, for instance. So here I just enumerate what's in my set, and it can be anything. I can say it's numbers, it can be matrices, it can be other sets, it can be mixtures of different mathematical objects, whatever I choose. And important note, the order doesn't. Oh yeah, so question, what's happening with the tutorials? Well, I just spoke with the TA yesterday, and yeah, so they start in 2 weeks, and she said, so I'm not going to give you exercises after today, not because I don't have any, but because, well, I don't have any now. She's going to send me some exercises so I can see what was done in the last years to look more or less what was asked of the students. So I should post them as soon as possible. So you can practice on them. Oh, did they start next Friday or the Friday in 2 weeks? I thought they started next in 2 weeks. Yeah, week 3. Yeah, that's what I think.
Sorry, I just have a question for the tutorials.
Yeah.
I had a clash with one of my classes and I would not be able to attend the tutorial, but I did want to go. Is it possible that they could record and we could watch it after?
Yeah, I can ask her.
Yeah, that would be great because I wanted to go to the tutorials as well just for extra help.
Yeah, okay.
Yeah. Thank you.
No problem.
Just another question.
Yeah.
Is it possible to have the tutorials online on Zoom as well?
Yeah, they are online. Yeah.
Okay.
Yeah, they're all classes online.
Okay, thank you.
Yeah, that's the thing with Zoom. Once you start getting used to it, everything is, oh, can we meet? Yeah, I could drive, or I could take a bus, or let's just meet in Zoom, and everything is in Zoom, so everybody stays at home. We don't meet anymore. So that's convenient, but that's also, yeah. So everything is in Zoom now. So the whole class is in Zoom. But again, if you want to meet in person, I have my office hours on Fridays. So yeah, today at what time? Yeah, the same hour, but so in my office. Okay, so that means that is this exactly the same as 315. So it's a bag of object. So if I mix the bag together and the object change order, it doesn't matter, it's the same thing. Which will of course not be the same for for other things that we see. And we can also describe them. So by description. So I could say the set of all integers that are larger than 2. Yeah, strictly larger. To be, it's a math class, we have to be precise. And I'm going to say what I mean by that. So it would be S. So let's see, this is S2, that's just the second example, or S2 maybe. Equals to X. So X is an integer such as X is in N and X is greater than 2. So what do I mean by strictly or strictly larger, strictly greater than 2? I mean this thing. So this is strictly greater. This is strictly smaller. This is greater or equal. If I don't say anything, assume that equal is there. But yeah, I should normally be precise when I say things. Yeah. But if we say strictly, then it means that we exclude the limit, the boundary. And here what that means is that 2 is not included in my set. So it would be something like 3, 4, 5, ... And of course, ... You're allowed to use it as long as it's clear what you're saying. So here, for instance, I told you that I was talking about integers, and it's obvious that 3 and then 4 and then 5, so the other one would be 6, etc. So in that case, you can write ... So in your exam, if it's obvious, you can write it, but if it's not obvious, then write it in some other ways. Okay, and other thing that I was talking about. So what is this? This means such that. It's a description. Can you? Is that some math notation that is acceptable or not? Because I'm following the book now. So just to make sure. So the question is this. So can we write
That's just what I've seen on some other, like that's how they write it on Wolfram Alpha, for example.
Okay, all right.
Some
So
other places, but
in that case, I would have to say yes. But as I said, my formation is in math, so I don't know all the ways that mathematicians write things. So I start with the book and I stick to it as much as possible to make sure that we have a coherent way of expressing things. But so if you tell me that it's a acceptable way of writing things in math circles, then I have to say then yes, you can write it this way. Exactly. Oh, and also if we say and, There's also some other way of writing it, which would be, I don't know if I have the symbol there. Let's see. Yeah, I don't see it. If I don't see it, it's because people don't use it all that much. But the symbol for n might be. Try it. Show it to you. Suppose it's this symbol too. But so you might see that sometimes, and or it's the same symbol but reversed. So that's a really mathy way of writing things. But again, I think we're always going to write "and" here, and it's fine. So don't bother about this. Okay. Oh, and finally, this is is element of. So this means X is an element of the natural numbers. Yeah, lots of symbols, but we can get to used to it. Yeah, and also everything I'm writing. So if it's clear from the context, sometimes you can omit it, and even in math papers. So last paper I wrote was a math paper actually, and so at first I was super careful because I don't know too much. I was writing all the sets and all the description for everything, and then I went back and read the sources, and I realized that many times mathematicians don't write all that many details because they know amongst each other that, yeah, of course, this is an integer, this is, so you don't have to be always super careful. But so in exams, I'm going to at least try as much as possible as to see clearly when I want you to write things in an exact manner or not. Even the book sometimes writes things, and I'm like, oh, is that the best way to write it? Not sure, as long as it's clear. It feels strange to say that because I just told you that math was used to make sure that everything you're saying is perfectly clear, and still sometimes there are disagreements within math circles. So for instance, can S be an element of S, for instance? You can have a set of sets, but then there's a debate within mathematicians. Can a set be an element of itself? It sounds very strange. And some mathematicians in the 20th century didn't agree, but then some others said, oh yeah, but you can have the set of all sets, for instance, which would maybe by definition include itself. Well, that's more of a philosophical question than anything. But so we won't worry about these things for now. Okay. So other example, so the reals strictly or let's say not strictly, reals between -5 and 5. So how would we write this? We would write, so our third set is 3 equals 2. So somebody has an idea. So copy this this model. Well, so I can tell you, actually, that's something that in the book they say that you don't have to write. Like I just told you what are all the sets there, but for some reason in the book, Chen and Wainwright, sometimes they don't write it. They don't write all the sets in which they are the member of. So for instance, here they would write something like X such that -5 smaller than X smaller than 5. So they would just write it this way. They would not even write that X is element of instance. So, I mean, if we know from the context that X is a real, then you can just say that. Because we know we don't have to add this information, but you see that there's not one good way of writing it. Sometimes it's best to specify it, sometimes not. I mean, you can never go wrong if you specify more assumptions. And then I could say strictly between -5 and 5. S4. And what should I change? If I don't have a suggestion, I'm going to ask somebody at random. Question is, should I change? To get something that is strictly. No takers, all right. So let me select a victim at random. Let's say Jimenez Edinson.
Yeah, I'm here.
So what should I change for this to be the real definition?
Maybe the instead of putting negative is smaller than X, like -5 is smaller than X, maybe put it like -5 is smaller and equal to X, and the other
Yeah.
side.
Exactly, perfect. Perfect.
Sorry, I'm just a bit confused on that. I'm like strictly, isn't that without the equal? So why are we adding the equal?
Oh, yes. So you're right. Yeah. So that's why nobody answered. Sorry about this. Thank you. No, the real way professors handle their mistakes is they say, "Ah, but I was testing you. I was seeing if you were aware of."
Just a question. So if it says it's between -5 and 5, that should be anything other than those numbers. So why are we taking greater than equal to, which should include that number as well?
Say that again.
So when we say it's between -5 and 5,
Yeah.
that means it's anything but those numbers. But when we say it's greater than and equal to, that means we're including -5 as well and 5.
Yes, strictly means that we don't include the limits.
Yeah, but no, just the second one, the reals between 5 and -5 and 5.
Yeah.
But then between is anything between 5 and -5 and 5, which should be -4 to 4, right? And it should not include -5 or 5. So why are we including equal to?
Well, so that's what I'm saying. So between here, I'm not saying that it's strictly. So it means that it includes the boundaries as well.
Okay.
Or I could say, yeah, I could write it this way. Or yeah, it's just a convention. I'm not saying that's actually that's what it should be. I'm just saying that's what really normally people refer to. It's when they really want to exclude boundary, then they say strict.
Okay.
All right. So a question for you. Oh yeah. So another symbol definition or other symbol. So this means included or is a subset of. So this means that something is part of something else. So a set is included in some other set. So then question is S3 a subset of S4? S3 is this, S4 is this.
Yes.
Yes, good answer. Yes. S4 is S3 with -5 and 5. So here I'm just writing it this way because I haven't defined other things, but we're going to define union, intersection, and all this good stuff later on. Yeah, then some other thing that I could, other symbol. So this is the empty set. So it means a set that has nothing inside it. So like if you imagine that a set is a bag of objects, then it's when I have removed everything from the bag, then there's nothing in it. There's air, but we assume that air is nothing interesting. So then, and one convention is that the empty set is a subset of any other set. So because any bag with stuff in it has also emptiness in it, if you want. All right. So then question, well, I just told you, but can we say that empty is included or is a subset of say S3, and yeah, and then the question is, of course, yes. I could see a subset of any set. Now something I could say, is this true? Well, that's a convention again. And the convention is yes. So one subset of a set is itself. So a subset. Yeah. Subset of set is itself. So what are the subsets in 1, 2, 3? So subset of 1, 2, 3. We get empty set. We get one element sets. So 1, 2, 3. Two element sets. 1, 2, 1, 3. 2, 3. And three element sets. So 1, 2, 3. All right. And then while you were copying all of this, so question for you. If a set has n elements, how many subsets does it have? So that's a difficult one.
Is it 2 raised to power n?
2 to the power n?
Yes.
Yes. Why? So yeah, for instance, here it works. It's so
I
2
would
to
say
the 3.
it's okay. Sorry.
Yeah, go ahead. Go ahead.
I would say every like set has two subsets, one unknown and then one the element itself.
Yes, exactly. So here's an intuitive way of putting it. So intuition. Empty set has one subset. Then every time we add a set, an element, maybe in every subset or not. Oops. Every extra element, every new element. So for instance, if I consider the set 1, then I add 1 and I could have either empty or 1. And then I add 2 and I could have empty or 1, empty and 2, 1 or 2, etc., etc. It's a sort of proof by induction. Yeah, so by induction, how I should say this, a proof by induction in a few words is I show that something is true for a base case, and with some rule I can show that given that it's true for a base case, it's true for the next case. So in that case it would be it's true for subset, then it's true for a set with 1 element, with 2 elements. So if it's true for n element, and then it's also true for n plus 1 element, then I can say that it's true for however many elements I have. That's an intuitive way of describing proof by induction, but don't worry, we're not going there. Is that clear? Or does somebody have a question about this? Because this is not obvious. You have to think about it. Okay, well, come to office hours if you're confused. I'll explain again. All right, so operation and sets. Oh, by the way, when is the class finishing? I don't want to go over time.
11:30.
Oh yeah, 11:30. All right. Operation and sets. Union. A set formed by the elements in either of 2 sets. So for instance, I could write 1, 2, 3 union 3, 4, 5, 6 would be equal to a set which would be X such that X is included in 1, 2, 3, or X included in 3, 4, 5, 6, and is of course equal to a set which is 1, 2, 3, 4, 5, 6. Right? I probably for most of you, it's you already have seen a union before. Intersection. So what is intersection?
It's what 2 sets have in common?
Yes. By elements common of in 2 sets, or present in either in both sets. So we write it. like this. So this is, of course, union. So it's a U. So that's how you remember it. And intersection, that's a U inverted. And by the way, if you go back to what the drawing I showed you for and, so and was like this, and or was like this, and n was like this. So it's kind of the same thing. So here it's or, because it's in this set or this set, and here it's in this set and this set. So what would it be? 1, 2, 3. Yeah, so there's only 3. So it's a 1 element set. Okay, so yeah, a lot of definition today, but yeah, don't worry, we're getting to something more tricky. So a universal set. A set of, of all considered element. So what this means is it's the totality of what interests me. So if I'm only interested in the numbers 1, 2, 3, 4, then the universe is 1, 2, 3, 4, and the only sets I can have in this universe is combinations of these elements. So example, U, which would be known, the universal set would be 1, 2, 3, 4. So why do we give it some special name? So this is just to be able to say, okay, what's outside of a set? Well, what's outside of a set? What's outside of a bag that I have in my hand? Well, it's the whole universe, the whole world. So it doesn't tell me a lot. But if I've defined the universe to be 1, 2, 3, 4, then, and if I have a set that contains 1 and 2, then what's outside this set? It's the rest, so 3 and 4. And that's just what I'm going to describe. So complement is going to be elements in the universe, but not in a set. And we note it this way. So we put some tilde over it. So it's in some notations too for not, if you have some proposition and you want to say not true or not this proposition, then you have a tilde in front of the proposition. So this is the sort of equivalent for sets. So if we want to ask what is not in the set, so we put a tilde over the set. So for instance, if I have this, so U is 1, 2, 3, 4, and so some set, let's say it's S5 now, equals 23. Then not A is equal to, so I can just, this is, I'm writing this just to, again, always use the same notation to become familiar with it. So X, such that X is element of U and X is not element. So when we say not something, then we have to, I don't have shortcuts for that. Not element of A. And that will be equal to then what? What is not A there? Let me ask a victim if I don't have somebody who saves the group.
Well, it'll be a 1 and 4.
Yes, good, thank you. 1 and 4. Some other question, then what is not you?
All
Some other-
reals other than, oh,
So I've said here the universe that I'm interested in is just 1, 2, 3, 4. So I'm not saying that there's something outside you. There's nothing outside you. It's like, or there's the multiverse, maybe the multiverse of all other sets. But for now, this is yeah. So I should say the universe. So in that case, not the universe. What do I get?
Not the empty.
Yes. Empty set. So if I ask what is not anything, well, it's nothing. Good. So questions about these rules? No, everything fine. All right, so let's go ahead and see some laws. So, commutative law. I'm always going to do that for union and intersection. So, A union B for some set A and B is equal to B union A. So that's pretty obvious. So if I start with something and I add together, add the missing element from the other, then it's the same as starting from the other and adding the missing element from the first set. And so that's the same for intersection. So A inter B is equal to B inter A. So this is quite intuitive. Now, distributive law. Union B union C equals to A union B union C. It's also quite intuitive. So if I'm going to put 3 things together, then if I start by putting these 2 things together, then I add the third one, then it's quite intuitive that it's the same as having these 2 combined together and then adding the third one. Or it would also be the same as A and C union B. Same thing with intersection. So if I want the common elements of 3 elements, then whatever the order I take their common elements. then it should give me the same thing, right? And then, but then the tricky part, combining union and intersection together. Can I do that? Will it work? So can I write this, for instance? A union. Oops. So instead of B union C, let's take B intersection C. Would that be equal to, let's put a question mark, to sorry. A union B intersection A C. So what do you guys think? I would like to take a vote on that. Can I take a vote with oh, yeah, I have this. Never tried it. Oh, no, it's complicated. Okay, let's forget about this. So can somebody say that they think yes or that they think not?
I think Isaac's writing in the chat.
Oh. Oh, yeah, I think maybe let me check the textbook real quick. I think you may be right. No. Thing is, I think that's the other. Yeah, so this is the distributive. This is the associative law, and this is the distributive law. Okay, yeah, so that's good. Sorry about that. Yeah, so should I associate B and C before associating A, or associating A and B together, then C? Yeah, so that makes sense. So is that, Patrick, are you saying it doesn't work? So you're saying this is false?
Yeah, I was saying it's false because if you're taking the union and then the intersection, you're taking like you're taking the union of A with the intersection of B and C. Oh, and then you're saying the union of A and B, and then intersecting that with the union of A and C. Okay, yep, yep. No, I see how that works, but
You see that works? So
yeah.
I can't see how that works. So it's just this is intuitive in my mind, but this is getting too complicated. So when I looked at
Yeah.
it, I thought, okay, how can I? So if you, that's something that I can tell you in your career as mathematicians or economists, you will get to see a lot of things that look really weird and too complicated. So in that in this situation, what you have to find is some way to simplify things to understand what's going on. And so how did I manage to check whether this is true or false? So one way to do it would be to use Venn diagrams. So, and then once you see it on Venn diagrams, then writing down a proof that this is true would be quite easy, in my opinion. So let's
Yeah, that's what I was doing. I needed to put it in Venn diagrams to show that it works.
Yeah, exactly. So let us just do that. So let me share a screen. All right. So imagine I have 3 sets. So we are not geniuses. It's normal to not see something abstract like this right away. So we just have to check it for ourselves. A, B, and C. Here I have A, B, and C. All right, so what is the first proposition? It's A union B intersection C. So A, I think I don't have a, how can I, okay, yeah, I know what I'm going to do. Okay, so this is A union B inter C. So let's start with this since it's inside the parenthesis. So B intersection C is this thing, right? This section there that's common to B and C. Yeah, I'm doing my best, but that's not like using an iPad. But yeah, it works nonetheless. So this region right there, this is B inter C, right? It's the common element of B and C. And then I take the union of this thing with A. And what is the union with this thing and A? Well, it's this plus the rest of A. So this is A union B inter C. Okay, now let's check the second one. A union B intersection A union C. What is A union B? It's this plus this together. So let's use red again, why not? Oh, sorry. Zoom that in my way. And then let's use yellow. Wow. Okay, that's a challenge. All right, so this is A union B, and this is A union C. What are the common elements? B inter C and A. So is that true or not true? That this is equal to this?
It looks like it's true.
Yeah, it's true. So, but it's, if you couldn't see it, that's just being a normal human being. I couldn't see it either. I had to draw a Venn diagram to be sure. So yeah, that's true. All right, second, then let's revert things. Is A inter B union C equal to A inter B union A inter C? So do it on your own and then tell me what you get.
Can you switch the screen back to the
Oh,
notes?
sorry. I'm looking at it right now, but yeah, there it is. Sorry. I just flipped the things around. So A inter parenthesis B union C. Oh yeah, by the way, I haven't defined parentheses. So by the way. Indicate priority of operation. So what's inside is done before the rest. Somebody wants to commit an answer?
I believe it's true.
Yeah, I think your belief is justified. So let us try it. Okay, so sharing my screen. So here, let's have this, which will be, okay. A, B, C, A, B, C. So let's start with B union C. It's a bit pale, but we can see that. And then intersection with A. So the common elements of A and B inter C would be these two, or these three sub-regions. So that would be, let's use green. Oops. All right. Second way of doing it. A inter B union A inter C. Well, A inter B is this region there. So yeah, let's use green. And A inter C is this thing there. And since we're going to take the union, so let's use the same color. And do we get the same thing? Yes, we do. These two. And so if you wanted to write a formal proof, I've never seen it, but one simple way I would say is to just define subregions. Say this is small a, small b, small c, da, 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 da. And you can just use these things to show that these two should be the same. That's my my intuition of how I would go about it. I don't know if it would work. But... Okay, so is that clear? So Venn diagrams, very good. If every time you're kind of confused about something, if you find a way to make a drawing, then it's just so clear. Okay, and as I said, I was super confused when I saw that first time. I thought this is black magic. There's no way this it's true, and yet if you try it, then it becomes obvious. Okay, so we have 12 minutes left. So let's see where we are. All right. So some examples. So if, so this is going to be easier. This is just application. A is 1, 2, and 3. B is 3, 4, and 5. And yeah,
the screen is still the same.
you're saying B is the same?
No, you didn't switch the screen back.
Yeah.
Oh,
the-
thank you. Sorry about this. Yeah, so we're just going to have some examples of all of the things we've been talking about. Okay, 1, 2, 3, 3, 4, 5, and C is let's see, 1, 4, 7. So let's look at A union B intersection C. So that would be equal to what? To A union B inter C, which would be, what is B inter C?
It'll be 4.
Yes, thank you. 4. And A union 4 would be 1, 2, 3, 4. Yeah, sometimes I ask questions that may shock you because they're too easy, but you know, so I ask the questions I ask. All right, so let's try the other one. So yeah, let's try A union B. Intersection A union C. So that's equal to, yeah, so I'm just going to do it myself. A union B, that's 1, 2, 3, 4, 5. And A union C, that's 1, 2, 3, 4, 7. So that's, and then the common element is yeah, that's oh, here I didn't, yeah, screw this. So 1, 2, 3, 4. Yeah. And we have just shown that something is true all the time. So if something is true all the time, then at least it should be true some of the time. So here there's an example where A union B inter C is the same as A union B inter A union C. We get 1, 2, 3, 4. All right. And then did I have other things to show? Yeah, I'm kind of done actually. So I don't want to start another chapter, but I have a quiz for you. So in the remaining time, please do this quiz. So I'm going to put that there. So, but you know, of course, it doesn't count. So it's just for fun. So hopefully it works. So you just click on that and answer to the best of your abilities. So probably that takes much more time than the time left, but you can take your time, and then the next week you're going to see what you wrote. And grading it will be a good way to check whether you Not grading it, but just looking at the answer will be a good way to see if you understand or not. Yeah, some are, you know, you do your best. So, some are tricks, some are, yeah, I don't remember what I wrote actually. Let me check. Oh yeah, I use emojis just to change it. Bonjour, monsieur le professeur. Presque fini. Oh, you have to, do they ask for something? Let me check. Well, you can write anything. It's not graded. I just want to have a sort of idea of how you. No, you don't. You just do it. I just want to see how you guys do in general. Last one, given any set S and a universal set U, what statements are true? So S union intersection equals beer. So so it has to be true for any set S. So is it true that it's going to be true for any set S or not? So S inter empty set equals empty set. S union S equals, oh yeah, I think I didn't want to write the third one. I wanted to write S actually. Let me try to edit that. Yeah. Oh no, that's true. I wanted to write U. Yeah. No, so no mistake. S inter S equals empty set and S inter U equals S. No, do your best. All right, so it's about all the time we have. So next time so I'm going to send you some exercises, hopefully soon. And next time we can just check at the answers of that and then continue with the tuples and order set and all that good stuff. So questions before you leave? No, all right. So I see you next week.
Thank you.
Thank you.
Thank you.
Bye-bye. Thank you.
Bye.